All right, let's talk about some artificial intelligence. This video is just going to be a general recap of two videos I recently saw and just, we discuss a bit about it. It was a one about universal approximation theorem by Vizuara and one about neural networks by Three Blue One Brown. If anybody's interested in their more comprehensive guide, because frankly, mine isn't gonna be very in depth, lecture about these topics, feel free to visit them. I'll link their videos in the description. But without further ado, let's get started. All right, so let's start off with Vizuara's video about the universal approximation theorem. I used um I used some AI to help me make these diagrams to help illustrate these points a bit easier because some of the topics are very advanced for what they were, and his video went very math heavy, which this simple discussion doesn't have a place for. So, the universal approximation theorem about neural networks and function approximation. So, the universal approximation theorem is broken into three separate components, and these components can be neural networks, function approximation, and activation functions. All of these split up into their own portions as well. As we can see, neural networks go into the hidden layers and the neurons as well. And then the activation functions go into ReLU, a type of function used in these types of in these types of machine learning, and then sigmoid functions as well. And then function approximation, we see that there's continuous functions, and then there's also complex curves. Okay, so that's all a bit to take in. So let's see what this all means. So what this theorem basically says is that a simple neural network with one hidden layer can copy or approximate almost any continuous function. So this works if the activation function, which is a special math rule the network uses, is the right type. Excuse me, I'm not used to this. I am reading a script, so okay, so why does this matter? Why is it important? Why is it cool? Or why do I view it as being something pretty cool? So if we think about a neural network as a powerful tool that can break down complicated things like shapes or curves into simpler parts and then piece them back together, this is what makes neural networks so useful in solving problems like recognizing images or predicting things. And then we talked about how it works. So let's talk about some pros and cons now. Okay, so some pros and cons to neural networks and the universal approximation theorem. So some of the pros include the fact that it's versatile. There's versatile function approximation. It simplifies complex problems, and then it's also useful in various applications. Okay, so what are some of the cons, you may ask? So some of the cons in this example are that it requires specific activation functions. It's very limited in that aspect. As we talked about before, it does require very specific ones. And then it also its performance depends on the network size, so its performance can vary a lot. And then there is potential overfitting issues involved as well. So let's talk a bit more in depth about this. Okay, so neurons are like little calculators, and the neurons are what we discussed earlier in this in right here. Neurons is part of the neural network. So this he discusses in the video about finite neurons, but let's talk a more general view over here and why it pertains to our specific topic right now. So, like I said, neurons are like little calculators. By adding more neurons, the network gets better at copying functions. And for example, it can turn a really complicated curve into a. Let me just resize this for myself here. Okay, it can turn a complicated curve into straight line segments that fit together really well. So it turns this very complex curve, otherwise it'd be very complex, like we're saying. It turns that into a very simple one that we can digest. So and then we can talk about ReLU functions as well. So let's go to the third slide. Okay. Like I said, nodes can act as small calculators that improve function approximation by adding more processing units. And then I went a bit more in depth right there. Okay, so the ReLU function. We've brought this up a few times, and the video that I'm referencing brings it up a bunch of times. So a simple version of this is that the ReLU function modifies inputs by turning negatives into zeros, enabling the network to form complex shapes. Okay, so that doesn't exactly tell us what the, like on the lowest level, what a ReLU function is. So what a ReLU function is ultimately is it's a common math tool used in these networks, in these neural networks. And it like I said, it turns negative numbers into zeros and then leaves the positive numbers as they are. So, and then we can combine these multiple of these ReLUs to create like these complex shapes or curves in these neural networks. Then um and then using ReLU in neural networks. There's pros and cons to both approaches here. So the pros include enabling non-linear problem solving. It gives us more approaches to the problem at hand. And then it also approximates complex functions. So complex functions that we would otherwise not be able to solve, or it would take a vast amount of resources to solve. But then the cons come with limited range, and then the performance drops outside of that range. So it's a very limited range of what we can use the ReLU functions in like these neural networks, and then outside of that very limited range already, the performance is basically takes a nosedive. So it goes from being very consistent to just plummeting all the way down. So the video shows like how a neural network can copy a cubic function. In the example he showed, it was a curved graph. So by using the ReLU functions and some math, the network gets close to matching the curve. But then the limitations arrive here as well. Excuse me. The network can only mimic functions in a specific range. If you go too far outside this range, it stops working well. Excuse me again. Without special rules like the ReLU functions, the network wouldn't be able to solve nonlinear, in this case, the curvy lines, the curvy problems. This makes activation functions super important. All right, I will cut here, and then we will resume with the discussion about the second topic. All right, let's talk more about neural networks. So now we're going to be moving on to discussing about 3 Blue 1 Brown's deep learning chapter 1 video about what is a neural network. So to address the question of the video, first of all, what is a neural network? So a neural network is a structure that processes information in layers. So these layers include the input layer, which takes in the data. It could take in something like a picture of a number, for example. Then there's hidden layers. So these layers break the data into smaller pieces, and then it attempts to understand it, so into like digestible chunks. And then there's the output layer. This layer provides the final result, and then like in the example that we stated before, a picture of a number, it identifies the number as a 3, for example. Okay, let's speed this up because I don't want this video to be too long. But what do neurons do? So neurons within the network hold values between 0 and 1, functioning similarly to dimmer switches for light bulbs. As the network processes the input, these values change, allowing the network to adjust its understanding of the data. As you can see from the picture, neurons activate by holding values between 0 and 1, and then there's the value adjustment, and then also the data understanding. All right, what about the learning process? The neural network learning process. So the learning process involves several key components, and these key components are stuff like each connection between the neurons having a weight, and what this weight it does is it acts as a multiplier, and then neurons combine these weights, their inputs, and then an additional number known as bias. So after the bias, they apply an activation function, which in this case would be ReLU or sigmoid, like we've discussed earlier. to determine whether to light up or remain inactive. And then during the training, the network adjusts these weights and biases to improve its accuracy in providing correct answers. Okay, why is training these neural networks so hard? Training a neural network can be challenging for a few reasons. Or not few, but like a lot of reasons. Because the number of weights and biases, there's a lot of them that can be adjusted. So this can result in having to change like tens of thousands of values. And because of that, the training process is crucial for helping the network discover the optimal values for these parameters. Okay, so for instance, when the network is presented with an image of a 3, like the video discusses, it activates specific neurons in the hidden networks to identify patterns such as loops or straight lines. Over time, it learns to associate these patterns with the corresponding number. Okay, let's talk about our two functions. Our two of the activation functions we've been talking about a lot. ReLU, which is the rectified linear unit, and sigmoid functions. So as you can see from the little uh, picture, we have ReLU in a positive light, while sigmoid is kind of in a negative light right now. So the reason for this is because ReLU has gained popularity due to its simplicity and effectiveness in facilitating the learning process. On the other hand, the sigmoid function, while it has been historically significant, is less favored in modern applications because it can complicate the learning process. So, just for the ease of use, and then sigmoid functions just overall complicating the learning process, we opt to use ReLU nowadays. All right, well, that's my general view of, or my general discussion about deep learning, machine learning, just artificial intelligence in general. Once again, if you want to learn more about the topic, just look at the description. I'll make sure to link the videos because they go in way more in depth than I do. And that's it for me. I'll see you guys later.